So now we have the second part. And in this second part, we have yet other 6 approaches that describing how they calculate the diffusion coefficients and what they get for RAA and V2 in general. The first one is the approach from Catania, and there will be Santosh Kumar Das that will describe the approach. Santosh, do you have the microphone on? Yes.
Yes. So should I start?
Start. Yes.
Start. Okay. So good morning, good afternoon, good evening. First of all, I would like to thank the organizer for providing us this opportunity to present our work. So here I am talking on behalf of this Catania group. Yes, and mainly I will discuss about heavy quark diffusion coefficient in QGP. So here my major focus will be how we are constraining our transport coefficient using lattice QCD results as well as experimental data. So to compute the heavy quark drag and diffusion coefficient in QGP, we are adopting the Fokker-Planck approach. And this Fokker-Planck equation can be obtained from the Boltzmann equation under small momentum transfer by expanding the collisional terms in terms of the loss and gain. And here, AI is our drag coefficient and Bij is our diffusion coefficient. And here, how we are computing the drag and diffusion coefficient of the heavy quark, considering the elastic interaction of the heavy quark with the bath consists of light quarks and gluon. So to compute the heavy quarks drag and diffusion coefficient in QGP, we need several inputs like the scattering matrix, the coupling, the device skinning mass to shield the divergence associated with the T-channel diagram, as well as the light quarks and gluon masses. So for this coupling as well as light quarks mass, as well as the light quark gluon mass, we are using a quasi-particle model. So this is a way to take into account some of the non-perturbative effects and going beyond the PQCD approach. So by fitting the lattice QCD energy density and pressure, so what here we are doing, we are just enforcing the energy density within our quasi-particle model is equal to the energy density of the lattice QCD. Then we fit the coupling constant as we have noted here, and here is the gluon as well as the light quark mass in terms of the coupling constant. So here, in fact, we fit both the lattice data from Upetal Budapest as well as the hot QCD collaboration, but here the value we have noted mainly for the Upetal Budapest group, and this is the quasi-particle model which we are implementing in our calculation to compute the heavy quark transport coefficient. And this is the variation of the coupling constant obtained within the fit, and this is the various temperature variation of the light quarks and gluon mass. So here I will just like to mention this calculation we did without using within the on cell. So we did not consider the width, but recently the Catania group also extended their quasi-particle model, including the off-cell dynamics, including a width. Just like to mention, by including the width, it only affects the transport coefficient in the low momentum domain. If we go to high momentum, say 2 to 3 GeV, its impact is really negligible. Then with this input from this quasi-particle model, we proceed to compute the drag and diffusion coefficient. Here, another thing I would like to indicate, as we can see here, our coupling is vary with the temperature, not with the momentum. That's why we always constrain within the low momentum domain. So we have never tested our model beyond, say, PT 10 GeV. Then we solve to study the heavy quark momentum evolutions in QGP, the Boltzmann equations, considering the two-body collisions. And in this Boltzmann equation, the input is the matrix element, not the drag and diffusion coefficients. So here we use the matrix element. With the input, we obtained it within the quasi-particle model to study the heavy quark momentum evolutions in QGP. And we implement this Boltzmann equation within a stochastic algorithm. Then also, we also solve sometimes the Langevin dynamics for the sake of comparison to study the heavy quark momentum evolution in QGP. But in this Langevin dynamics, the inputs are the drag and diffusion coefficient obtained within the framework of the quasi-particle model. And also, we also sometimes use the PQCD with running coupling for the sake of comparison. But I would like to mention now we are moved more towards the Boltzmann equations, and we are mainly concentrate on the Boltzmann equation to fix the transport coefficient within our model. So to study the heavy quark momentum evolution in QGP and extract the heavy quark transport coefficient, we also need a bulk dynamics. So in our calculations, we are using a transport bulk. So within this transport bulk, our light quarks as well as our gluons are massive. And within this transport bulk, we can able to reproduce the bulk spectra as well as the elliptic flow. And here I have shown within our transport approach, here we have obtained the equation of state, both for the Rig as well as for the LHC colliding energy using this massive bulk. As we can see, within our transport approach, we can able to reproduce the lattice QCD equation of state. So with this setup, we proceed to further constrain our transport coefficient. So what we are doing, we compute the drag and diffusion coefficient or the matrix element in the Boltzmann equation, we put as an input. Then with this, we proceed multiplying a constant to explain the experimental data. Then we see at which value we can able to explain the experimental data. So here we first proceed to compute the nuclear suppression factor as well as the elliptic flow within our model, and we compare with the experimental data. So as we can see here, within this Boltzmann equation, we can able within our model, we able to explain the experimental data. And here I would like to inform these results are in 2017, where we have not considered the lambda C production into our calculation. We have not implemented. That means in this calculation, we consider all these charm quark converted to the D measure. So if we include the lambda C, certainly our array will change a bit. Then with the same framework, with the same transport coefficient, within which we able to explain the Rig data, we proceed to study the array and V2 at LHC energy. So as we can see at LHC energy also, within the same transport coefficient, same evolution equation, we can also able to explain reasonably well both the array as well as V2. Then further, we extend the same model, including the event by event initial conditions. Then with this event by event initial conditions, we also compute the higher order harmonic, say for example, the V3. So here also we have plotted the V3. So as we can see, within this model also work well for this V3, and within our model, we can able to explain this V3 as well. So then we proceed to compute this heavy light correlation coefficient as defined within this, as defined here. So as we can see, we compute this heavy light correlation coefficient. So as we can see, this heavy light correlation coefficient, the strength decrease with the higher harmonics. So here we compute both this light heavy correlation coefficient both for the within PQCD as well as for the quasi-particle model. But here we tune our model in such a way, in both this model we can able to reproduce the same array. But here the most important point is that as we can see here, this correlation coefficient is very sensitive to the temperature dependence of the transport coefficient. So we believe this is a novel way to further constrain the heavy quark transport coefficients going beyond the array and V2 dynamics. Then we further extend the same model Then we compute the event shape engineering for as done in the experiment at LSC energy, both at 0 to 10% centrality, as well as 30 to 50% centrality. And as we can see within our model, we can also again able to explain. Then also the same model, we also try to study the heavy baryon to meson ratio, implementing a coalescence plus fragmentation scenario. And within this model, we get a peak around lambda c by d around 1. And our model also works here, and we can reasonably explain the experimental data. So again, I will just like to mention with here all these result I have shown here, the few experimental result. Here we are using the same transport coefficient. That means using the same transport coefficient, we try to explain as much as experimental data available, and if we can really within the same model, same framework, if we can able to understand and constrain the transport coefficient. And again, our model also work for heavy quark dynamics in presence of magnetic field, where we compute the heavy quark directed flow, which we have not shown here. Then we have also extended the same model to compute the observable for a B meson at RA at LSC energy, and here we have compute the B meson RA as well as the electron decay from the B meson and compare with the experimental data. And here we have included lambda B to compute the array within the same framework. So then at the end of the day, what we are doing, so we are using transport coefficient as an input to our transport coefficient as an input within our transport framework. Then we see at which value of the transport coefficient we can able to explain the experimental observable. Then at the end of the day, we use that transport coefficient to compute the diffusion coefficient in position. That means the dx. And this dx can be computed either from the drag coefficient, or it can also be computed from the diffusion coefficient as well. So here we have computed it both for the charm quark as well as for the bottom quark, using both the drag as well as the momentum diffusion coefficient. But for the working group comparison, we have computed the dx starting from the drag coefficient. That means the solid line shown in this present calculations, and we have also used the same interaction for the bottom quark. So here I will just like to mention here our transport coefficient actually sensitive. What kind of physics we are including in our model, and if we are including some new physics, so it's impact our transport coefficient a bit. So thank you very much for your kind attention.
Okay, thank you, Santosh, for your presentation. Further questions? Seems no, it is.
I just want to maybe just ask this in all your presentation presented here. There is no radiative process yet, right?
No, we have only considered the collisional crash in this present calculation.
Yeah, okay.
Okay. If there are no other questions, we can go to the next presentation. That is from Frankfurt. There is Hendrik. When is Santosh, if you can.
Yeah, hi. I have to. Yes, okay. I try to share.
Hi, Hendrik.
Hello. I don't see myself.
But we see you. We see.
Very good. Okay, so I can be very brief because most was told by Ralph this morning, afternoon, however. Okay, so today I'll talk only about the heavy quark transport coefficients we used for, I don't know, 15 years or so. And I already jumped there. So, okay, this I don't need to stress again. This is the relativistic Langevin process. And I use a post point description, and then one can use a very simple Einstein dissipation fluctuation relation. And we adapted this B1, the longitudinal diffusion coefficient, because this was most of using our various potentials, or however you want to call it, to calculate these components. Okay, and for the medium, this is not for today, but for the medium, we use UQMD, hydro UQMD hybrid approach, and also UQMD with cross graining. And yeah, the first model we did in 24 or so was a simple quark meson model using chiral symmetry in the light quark sector and heavy quark effective symmetry in the heavy quark sector. So the very simple particle constant, starting with the d mesons and also some d stars. And of course the quarks, the light quarks and the heavy quarks. And yeah, for the interactions, it's this simple Yukawa-like interactions. And from heavy quark effective spin symmetry, we assume also these coefficients to be the same for the scalar or pseudoscalar and vector particles. And then, of course, you have this S and U channel contributions for matrix elements. And then, of course, the point was to have above TC some preformed hadron-like resonances, this D and B meson-like resonances. So we traced them with a one-loop diagram to have a finite width. But at this time, we did do this only on the vacuum. So these ingredients stay the same, and we vary our model parameters such that the T meson width is between 0.4 and 0.75 GeV. Also for the B and the MD and MB to 2 and 5 GeV. So with this model, we can go on, and yeah, these are the cross sections. And compared to PQCD, the point is they are more or less isotropic in this S channel, and this makes it much more efficient for the track and diffusion coefficients. As you see here, compared to PQCD, we have a factor of 3 or so enhancement. And yeah, and another thing what also Ralph mentioned, what will be stressed tomorrow more, is concerning hadronization. We usually use this coalescence fragmentation, but of course it would be much desirable to have this more recombination model, which we also already did when I was at TAMU, because there you have this resonances here, and there it's natural to do it in a kinetic way. Yeah, where you don't have all the shortcomings of the coalescence, where you have the entropy and so on. All these problems are of course gone if you use a true kinetic theory. But we haven't implemented this yet here. Anyway, the temperature dependence here, I don't vary, as I said, the particle properties with the medium, so it's simply increasing with temperature. This changes in this Brückner many-body approach, what was already told by Ralph this afternoon. In the beginning of the last session. So there we have this T-matrix approach, the usual ladder diagrams, or how you want to call them if you iterate this, and also the heavy quark propagator is self-consistently calculated by closing this loop here. And then as Ralph said, in this low momentum region, we can stay with the 3D Lippmann-Schwinger equation and then do a partial wave expansion, multipole expansion. Then it's not that expensive to calculate this T matrix. And but what you need is, of course, this this potential here, this kernel, so to say, of this integral equation. And there, as Ralph already stressed, we used at this time the two extreme cases. One is directly the free energy, and the other is the internal energy as a potential. And there, of course, this encompasses these are the two extreme cases of the free energy tends to be the weakest potential, and the U the strongest of all you can somehow extract from these lattice data. Then, of course, this Coulomb part for the other color channels. We used an anti-triplet, sextet, and octet channel 2. We just scaled this with the corresponding Casimir factors. And then you calculate this T matrix, and there you see the nice feature is that at higher temperatures there is nearly a continuum, so it becomes very broad, and then these resonances form. If you go towards TC, it's a bit like a Feschbach resonance. At this point, of course, you expect it to, at least in the crossover where everything goes smoothly from a partonic picture to a hadronic, then you expect that the bound states form, meaning, then the D mesons go below the heavy light threshold and form true bound states, and you go through such a Feschbach resonance. And of course, if this happens, then at lower temperatures you get much more coupling and also much larger drag coefficients. So here, this temperature here, it's shown as a function of momentum and for different temperatures. And as you see here for this T matrix resonance model, the order is flipped. So at a lower TC, you get a larger coefficients. And this was it already for today. And this I can mention, of course, everybody knows the tension between getting a large enough V2 and not suppressing too much in the RAA. And this is, of course, helped in this reversed order with temperature. So you pronounce the later stages to build up a lot of elliptic flow, but not suppressing too much. The suppression in the RAA is mostly to the early stages, so this is then better balanced, and the tension between these two to get these two quantities described right in comparison to data is a bit weakened. Yeah, this was it already for today from my side.
Okay, thank you, Henrik, for this presentation that goes really to the original idea also.
Yeah, I have not so much new to say. I'm sorry.
No, but I was, let's see if there are questions. My question is related also with the statement, because of course this is strictly related with also the presentation of Ralph, as you said. But at some point, Ralph was mentioning that there is still some strength in the transport coefficient that is missed, because there is some channel that should be considered and yet has not been considered.
Yeah, but yeah, what channel should this be? This is the question, right?
What? Sorry.
What particular channel should this be? What should we add? I mean, there must be some strength, right? Perhaps some, yeah, I don't know.
Okay, so maybe. I don't
Perhaps
know
Ralph can answer this.
Yeah, we have some ideas there. I mean, for example, there's long-standing debate in the literature as to what the nature of the confining force is, whether it's a scalar or whether it has vector components and so on and so forth.
Yeah.
Okay.
Yeah, but that's of course the big question about confinement. Yeah.
Yeah, of course, it's difficult.
Exactly.
Are there other questions? Okay. If not, thank you again, Hendrik, for your presentation.
Now I have to wait a moment. Where? Here, stop share. Okay.
And now we have the other approach, that is the one from Duke. I don't know who will present it. Fan?
Wenkai will present that.
Wenkai, okay. Thank you.
Yeah. Thank you. Can you see my screen?
Yes, we can.
Okay, great.
Yeah, you just need to go into full screen. Okay, good.
All right. Hello, everyone. My name is Wenkai from Duke University. And first, I would like to thank the organizers for inviting me here to present our study titled A Data-Driven Analysis for the Heavy Quark Diffusion Coefficients. This work is mainly done by one of our former group members, Yingru Xu, and I will be presenting the results on her behalf. So the basics of our heavy quark transport is this improved Langevin equation, which not only include the drag force and the thermal random force, but also the recoil force from emitting gluons by the heavy quarks. And this emission is calculated using the higher twist formalism, which has this gluon emission rate. So here the x is the energy fraction of the emitted gluon, and k perp is the perpendicular momentum of the emitted gluon. So we also have the Einstein relation, and those relations that relates the diffusion coefficients and the Q hat. So so what we generally use is this diffusion coefficient ds 2 pi t, which relates to Q hat by this formula. And in our study, we assume that this ds 2 pi t is a linear combination of two terms. One term is this perturbative QCD term, and the other one is this soft or non-perturbative term. And this non-perturbative contribution is assumed to be a linear function of the temperature of the medium, which is inspired by our previous study on shear viscosities. And we also have this additional parameter gamma, which controls the strength of those two terms. If gamma is close to 0, then this ds 2 pi t is dominated by the non-perturbative contribution, whereas if gamma is close to 1, then it is dominated by the perturbative contribution. So in addition to this improved Langevin equation, we also need other models to describe the whole heavy ion collision. So for the initial models, for the initial conditions, for the soft matter, we have this Trento model, which is a parameterized model for entropy or energy deposition. And for heavy quarks, we have this, we adopt this phono calculation, which is a fixed order plus next to leading log calculation for the momentum distribution of heavy quarks. And for the soft medium evolution of the QGP, we use this event by event plus 1D viscous hydrodynamics model called Vishnu, which takes both the shear and bulk viscosities into account, and it will later be calibrated on soft hadronic observables using Bayesian analysis. And for heavy quark transport, in this presentation, we will be talking about our improved long-driven model description, but we also have a linear Boltzmann plus diffusion model called LIDO, which we will be talking about on Thursday. And this is our model calibration or best fit to bulk medium observables. For example, the dn d eta or the Vn. And this calibration will be used to further calibrate our heavy quark transport coefficients. For hadronization, we use a combined model of recombination and fragmentation for heavy quarks. And later we also have a hadronic rescattering phase using URKMD to further propagate our heavy quarks or heavy mesons. So with all those models at hand, we want to answer the following question: given the models and the experimental data, can we constrain the model parameters? And the answer is yes, because we have this Bayesian analysis framework, which takes your model and then trains a surrogate model using a Gaussian process emulator. Then we have a Monte Carlo random walk through our parameter space, and we can extract the posterior distribution of our model parameters. Now the power of Bayesian analysis is we can use however model we like, and we can calibrate to as many experimental data as we have. But in this study, we will be using our improved long-driven model. So the Bayes theorem states that the posterior distribution of your model parameters, given some experimental data, is proportional to the likelihood function times the prior distribution. So the likelihood function is a probability of your model parameters of your model output equals to the data given some parameter set, and this probability will be smaller and smaller if your model output is farther and farther away from the experimental data. And the prior distribution is generally a uniform distribution over some physical range. And for example, the gamma parameter we talked about before is naturally constrained between 0 and 1. The Gaussian process emulator is a statistical model to quickly generate model output without actually calculating the model, because that takes exponentially time as your model parameters grows, as the number of your model parameters grows. And the Markov chain Monte Carlo is to perform a random walk through your model parameter space and extract the posterior distributions of your model parameters. So the experimental data we will be comparing to will be from the gold collision at 200 GeV and lead collision at 2 electricity energies. And observables will be comparing to mainly the meson RA and meson V2. And those are the model parameters will be varying in this study. So first is the strong coupling constant FS, and then the alpha, beta, gamma parameters that we use to constrain the DS coefficient. And the last one is the free streaming time, which controls the time between your between the initial condition and the onset of your hydro simulation. So before calibration, this is how the model output looks like. Taking arbitrary samples from all those model parameters, and you can see it varies greatly over the experimental data. And after calibration, this is the posterior distribution of our model parameters given those data, and you can see we have a quite good constraint on the coupling constant, on the strong coupling constant FS. It's around 0.3. We also have a pretty good constraints on alpha and beta and gamma. We don't have very good constraint on the free streaming time. We can only say it's around it's roughly between 0.2 and 0.8. And we can also use this posterior distributions to predict those meson observables. And you can see now the agreement with the data is quite good. And this is our prediction on this DS2 pi t parameter. The gray region is our prior knowledge before the calibration, and this blue band is our posterior distribution of 90% credible region. And this is in comparison to other model calculations of this DS, and you can see our extraction is quite consistent with other model calculations. And we can also use this extraction to predict other observables. For example, the meson V3, and you can see the agreement with the data is quite well. So, and that's the strength of this Bayesian analysis. And that's all for my presentation. Thank you.
Okay, thank you, Wenkai. Very nice talk. Are there questions? May I ask one thing? Essentially, you have this idea to get the DS as a combination of a part that is non-perturbative and another part that is like perturbative QCD, right? So, and then as a function of momentum, you determine the gamma that make one term or the other dominant. At larger P, of course, is dominant, the PQCD. But in this DS, as a momentum dependence, you put also a momentum dependence of DS, well, that is defined for P that goes to 0. But when you say DS PQCD, you get a kind of momentum dependence like in PQCD, or is something that is constant? And the only momentum dependence is the balance, I mean, the gamma square P square term. Yes, there.
Okay. Yes. So
these DS are just constant numbers, or they have, when you say DS PQCD, they have also momentum dependence?
Yes. So if you look at this, this two plot here, so you can see the DS2 pi t PQCD is dependent on the momentum as well.
Okay, and the other is constant. Okay.
Yeah, the other is constant because this one is so this linear one is the soft one.
So essentially, at low momentum, where you still get 1 over, let's say, p square dependence anyway, due to the gamma. That is, but at the end, the momentum dependence that you have, if I saw, was quite weak, right?
Yeah. So what we actually get is in between these two dashed lines. So those colored lines.
When Kai go back to the posterior distribution, to the results.
Yes.
One more. No, one more. Where you have the shaded areas here. Yes. Okay.
Yes.
So here, Vincenzo, you can see that for.
So the S essentially tend to go up, which means a gamma or an A that goes down, right? That is. But in the plot that we put together, when there is the Duke model, is the average value of this or is something else in what Shindong was showing yesterday, where there was AP, A as a function of P?
So this is the 90% credible region, but I think in the homework I gave you, it's the medium value of this ds to pi t.
Okay. Okay. Thank you. Other questions? Paul? Please.
Yeah, I already made this suggestion, Stefan, to you a couple of years ago, whether one could not directly kind of, instead of having those kind of laws, okay, with exponent and things like this, just simply take the ds coefficient as some kind of stepwise function, where you would basically take 3 or 4 values, like several pedestals, which might be a more direct way. Have you tried something in this respect, or do you think would be interesting?
Well, essentially each step would be an independent parameter, right? And so you would end up with a lot more parameters that a priori would be considered uncorrelated. And
you take the same number. I don't know that I don't say that you have to go for fine coarse graining. I mean, you can kind of take some values from 0 to 3, then from 3 to 10, and then from 10 to 30. No.
Yeah, okay. I mean, if we do sort of a really rough binning, which would correspond to the number of parameters that we have now, we can try that out. I just think that it's probably going to be ugly, given that the parameterization that we have does contain, some physics knowledge and expectations, how things grow or behave as a function of t and then p. Whereas if we just say, all right, for each bin, we just take one parameter, then this prior knowledge goes away.
Yeah, then it would be maximally data driven. That's the title of your talk. Yeah. Okay, good.
Okay, there is a comment also in the chat from Wei Yao, okay? It is a two-parameterization, the STP or kappa TP, so taking steps in T will cause problems in parameterizing, I guess, the momentum dependence.
Yeah, T and P wouldn't be correlated anymore properly as we have right now.
Mm-hmm. Mm-hmm. Okay. Okay, thanks. If there are no other questions, there are no, seems. So thank you again, Wenkai. And we go to the next talk that is from Ivan Vitev. Hi, Ivan.
Hi. Let me try to share the screen here and okay, so can you see the screen first?
Yes.
Okay, very good. So, okay, well, I would like to thank the organizers for the invitation. And so good morning or afternoon if you're in Europe. And I'll talk about soft SCET or soft collinear effective theory. So this was my understanding of what we'll discuss in the 3 days, roughly related to the 3 different tasks. So that's how I structured my talk. Maybe it's a little bit different. Before I actually go to the description of the theoretical calculation, let me make a few remarks. I see that the workshop is tailored toward transport approaches, Boltzmann, Langevin, Fokker-Planck, and SCET is not a transport approach, it's perturbative QCD. So by definition, it does not use diffusion or drag coefficients. Instead, what it can do is when we generalize it, take interactions in the medium, it can make use of the properties of the medium, which can be represented as an external field or potential. And then we can calculate radiative processes and branching. That's what SCET does. Also, a comment about applicability. So I was glad to hear yesterday, and I believe it may have come from Vincenzo, I'm not 100% sure, the transport approaches are applicable to low and moderate PT. And so SCET, on the other hand, being a perturbative approach, is applicable to moderate and high PT. So if I show calculations that go, let's say, below 5 GeV, this is an extrapolation in terms of radiative energy losses or branching processes. So SCET stands for soft collinear effective theory. It's an effective theory of QCD applicable in those momenta. And the way in which we calculate things is just like in high energy physics. We do higher order calculations and we do evolution. I was trying to make contact with the main theme of the workshop. And one thing that we can do is also take the soft balloon emission limit. And this leads to energy loss. We can evaluate energy loss, and this is the closest that we can get to some of the tasks. And this is what I decided to talk about in the 3 corresponding days. I also did not present, I saw that previous speakers presented a comparison to experimental data. I did not intend to do this at all. In fact, I don't think we have calculated hadron attenuation, DMB meson attenuation in the last several years. Those results are as of 4 years ago. We've mostly focused on the calculations of jets or other types of nuclear matter. But this just gives you one example when SCET, the derivation itself, together with the application, which is, as I said, high energy physics-like application, what kind of description of the spectra of the suppression of hadrons, RAA, you can get. And you see that in this particular calculation, couplings, that's the coupling between the jet and the medium, and also what enters in the medium transport parameters of the order of 2 gave a reasonably good description. Now let me go to SCET and SCET-G. SCET is an effective theory of QCD, and so we want to develop an effective theory applicable to heavy flavor, both open and quarkonia. I'll here limit myself to open heavy flavor, which is also applicable for different types of the media. We want to isolate the perturbative processes of parton propagation and branching from the non-perturbative physics of the media. And the effective theory of QCD, which describes jets, and subsequently it was generalized to heavy flavor, was developed by Bauer, Peugeot, Fleming, and Stewart in the early 2000s. It expresses the degrees of freedom in this effective theory are collinear quarks, those would be the energetic quarks, collinear gluons, also energetic gluons, part of the parton shower. There are soft gluons which describe recoil between, let's say, 2 final state jets. This would be relevant for correlations, not for energy loss or V2. for example. And this is the factorization formula that SCET uses. It's a convolution of a hard part, soft function. The beam functions are generalizations of the PDFs, and jet functions are the jets, or our heavy flavor in the final state. So the reason for which it has to be generalized is because there are modes missing in the effective theory which mediate the interaction between the energetic jets, or the heavy quarks, and the medium, and those are the Glauber gluons. Those are virtual gluon exchanges, preferentially in the direction perpendicular to the direction of jet propagation. They were first included for collisional processes, and so the part related to the quarks was written by Indilby and collaborators. And later we wrote down the full theory, including the collinear gluons. So these are the collinear quark and anti-quark fields. Those are the collinear gluons. And this is the coupling to the Glauber gluon, which mediates the interaction with the medium. Given a Lagrangian, and this is just the Glauber Lagrangian for the medium interaction, we can write down the Feynman rules and therefore perform calculations. Now, the original SCET as well as SCET-G was developed specifically for massless quarks. So we had to work harder to develop it for massive quarks. Mass was included in the SCET Lagrangian, and it was called SCET subscript M by Lebovich and Rothstein in 2003 and 2004. And it's important that this theory is formulated when the mass of the heavy quark divided by the light cone momentum is a relatively small parameter lambda, on the order of the relative transverse momentum versus longitudinal momentum in the jet. What we observed, however, is that when we do power counting in terms of the small parameter, which is what we do in effective theories, there is no crosstalk between the Glauber Lagrangian and the mass terms. Therefore, the resulting theory in the medium is simply a direct product of SCET M, which was developed for the vacuum, and the Glauber-Feynman rules, which were applicable for the case of in-medium interactions. And that saved us a lot of time. So what do we calculate when we have such theory? We calculate the splitting functions, or the splitting kernels, which take us from the hard scattering to the process of hadronization. So in high energy physics, this is what we need to do both higher order as well as resummed calculations. And those are examples of the heavy quark splitting functions in the vacuum. I've given the full splitting kernel both in terms of the transverse momentum of the splitting, as well as the longitudinal momentum fraction. And the reason is twofold. First, you have to see that here transverse momentum and longitudinal momentum do not decouple completely, even in the vacuum. And second, you see that in the propagator, there are those additional mass terms, and they're the dead cone effect, what was called by Dockschitzer and collaborators quite some time ago. What is not known, I think, by everyone is that the dead cone effect is different for the different branching processes. You see that here there is this X squares, and here there isn't. So one has to be careful when one does those calculations. Here is how a now medium-induced, that was the vacuum splitting function. This is how a medium-induced splitting function looks like. It's proportional to the property, depends on the properties of the medium. This is the gluon scattering length. If there isn't a medium, you can think that the gluon scattering length goes to infinity. And so this whole contribution vanishes. Depends on the momentum transfers in the medium, depends on the exact kinematics of the splitting. Those are the propagators. And finally, there are the Landau-Pomeranchuk-Migdal interference phases. And those interference phases, as you can see, depend exactly and very precisely on Kuiper, momentum exchanges, and the momentum fraction. So in principle, to take into account the full QCD physics of the Landau-Pomeranchuk-Migdal effect, we have non-local results. We simply cannot define it in a local way, because if we change a single variable, the formation lengths change. And so we have to integrate them out of the problem altogether. So what has happened since last time we talked at the previous meeting is that there have been other approaches to calculate splitting functions in the medium, for example, using the light cone wave function technique. It's traditionally used in saturation physics. And here's just one example in the vacuum. One can write the wave function for a quark, splitting into a quark and a gluon, and then tracing it, squaring it, and supplying relevant phase space. You can derive both massless and massive splitting functions. So that was kind of a really useful insight, because before we had to develop two different effective theories. Now in one shot, we can get both the case of heavy quarks as well as the light quarks. And of course, all results agree. So we have solid results which have been cross-checked many different ways. Now, this requires its own application going to next to leading order calculations or doing in medium Dirichlet evolution. If we have to stick to the full splitting functions and the techniques of high energy physics. For the purpose of this workshop, we can take the soft gluon emission limit. This is when the momentum fraction is small, and calculate the so-called energy loss distributions. So those will be the distributions of soft gluons emitted by a heavy quark, both in terms of angle, transverse momentum relative to the axis, and longitudinal momentum fraction. There was some ambiguity in the original calculations of heavy quark energy loss, what terms have to be kept here in the numerator, as opposed to interference phases in the denominator. And the fact that we calculated all other branching channels, in which case, in some cases, mass terms are clearly absent in the numerator, kind of gave us the insight which is the right limit to take in calculating the energy loss. Now, how are those splitting functions evaluated? For the latest calculations, and that's a change from what we had before and what I showed you earlier, we use as a background viscous hydrodynamics, Vishnu by Chunsheng collaborators. And here's just an example that these are not 30 to 50% collisions, these are central collisions. We take the space-time dependent temperature profiles, evaluate the device screening in quark-gluon plasma. We take two active flavors, by the way, if you're interested in this. We can calculate the scattering cross-sections, and those are the three-level quark and gluon scattering quark cross-sections on the quasi-particles in the medium. And we also calculate the mean free path. From this, this is what goes in our calculation. If we are asked, we can, for example, quote 2 times mu square over lambda and give you a transport coefficient. So here is what is in practice done. We calculate the fully differential spectra, both in X and KT, integrate over the gluon KT to get the intensity spectrum, then create the probability distribution for energy loss, and finally evaluate the fractional energy loss. And something that I wanted to note is that in the original paper with Kang and Ringer, we used a range of coupling constants between 1.8 and 2, but there we used an ideal Bjorken hydro. And so for this case, a value of about 2 worked well, and this is what I asked Xindong to put in the comparisons where we can make such comparisons. And so this is just an omission on my part. For the case of Chunsheng's hydrodynamics, we in fact get larger energy loss. It depends on the medium. And the reason is that the viscous hydrodynamics actually expands slower than the Bjorken hydro. And also we get like a larger transverse extent. So we also get a little bit more energy loss. So a G equals 1.8 will be a better choice if we want to compare what would be a best comparison to experimental data, which once again, as I said, I have not done plots. So this is just by eye comparison. So following sorry?
Yeah, just 3 minutes more or less.
Yeah, I'm getting there. So following this path of calculations, we can calculate the probability density. P of epsilon is the probability density, and epsilon is the energy fraction lost by the heavy quark due to multiple gluon emission. So we consider the process of multiple gluon emission. That would be equivalent for energy loss of Dirichlet evolution, in medium Dirichlet evolution, for example. And what is shown here is the probability for 5, 9, 16, 29, and 53 GeV quarks. And the way in which you read those figures is the following. So a broader distribution which is skewed more toward larger values of epsilon, would correspond to large energy loss. That would be the red curves. A distribution which is skewed toward smaller values of epsilon corresponds to small energy loss, and you shouldn't pay attention to the peak. Just kind of everything is normalized to 1. As I mentioned, this is a probability density. And finally, if I integrate over this probability density and weigh by the fraction epsilon, I get the average energy loss. And here is what we get for those values of G. First, at small momenta, we have, finite, but, kind of generally not the largest energy loss. The reason is twofold. One is the LPM effect, and the second is the heavy quark mass. The largest energy losses are at somewhat intermediate momenta, let's say on the order of 10 GeV, and then they gradually decrease as we go to higher transverse momenta. So I want to make just a few comments before I conclude. So QCD evolution in matter works in momentum space, not in position space. So all the integration must be, information must be integrated out. The reason is the LPM effect. Energy loss is simply non-local. Coherence lengths depend on all the kinematic variables, as I already explained, and they must be integrated out, and then the applications are in momentum space. Also, we cannot do calculations to p equals 0 if I present something below 5 GeV, so it has been extrapolated a little bit. And finally, I was thinking whether local drag, radiative drag can be defined. So this is the total fractional radiative energy loss. Can you define it per unit length? And the answer is really, you cannot do this properly. The reason, once again, is the LPM effect. Local radiative drag can be defined for Birch-Guinian radiation, which does not have the LPM. But on the other hand, Birch-Guinian, we know, does not describe the data. And that was shown more than a decade ago. And so, again, one can try prescriptions, but you're bound to get more or less arbitrary results. And let me just explain this point. Imagine that you asked to calculate energy loss in a box of certain size L. A box of constant temperature will get energy loss dependence that goes like L squared. And if we try to divide by one length dimension, you'll see that the radiative drag will depend still on the size of the box. So if you give me a small box, I'll give you one value for radiative drag per Fermi. If you give me a larger box, you'll get a different value. So this is what I wanted to say, and I wanted to explain, for example, why I cannot produce radiative drag type quantities. I can only produce integrated quantities like delta P over P. So thank you, and tomorrow I'll discuss the hadronization.
Thank you, Ivan. Very nice talk. Are there questions?
Ivan, maybe I just one question here.
Mm-hmm.
So, with you have this global soft glue exchange, which is the exchange between your heavy quark and the medium.
Yes.
And I assume in this case, your medium, you consider medium is consists of like thermal or either thermal parton or quasi-partons, right?
Yes.
And then the density is given by whatever medium you use.
The density is given by the thermal density, degrees of freedom T cubed, and
So essentially, whatever medium you use, whether it's hydrodynamics or So, but in that case,
gives the temperature profile, but then we use the temperature profile to create an underlying quasi-particle picture.
Yes.
So that we can calculate those cross sections.
So in this case, I think your global essentially is just like a transverse momentum exchange, but with no energy transfer. Like you don't have elastic energy loss in that case.
No, we don't have elastic energy losses.
That's true. But nevertheless, you can still calculate the transverse momentum broadly, like Q hat from this picture, right?
Yeah, absolutely.
Yeah. So that can be compare directly to other approach when they calculate the transverse momentum problem in Q hat?
Yeah, no. I mean, kind of. That's what I said. I haven't done it, but essentially if we calculate it, that there is a Gaussian part, excuse me, and then there is a logarithmic broadening part from the power law tails of the scattering. If we include the logarithmic broadening part, then for every energy, we have to start quoting a different value. I mean, it's in the calculation, but I don't like it. So the Gaussian part, which just depends on the properties of the medium, from this I can immediately plot what the Q hat would be. Right?
Yeah. Okay, I did just comment. I think there is if you want to make a connection to other models, this probably is a place to look at it.
I can plot again. The calculation that I showed and the code is written so that it integrates overall the expansion and the temperature changes. But I can, take a few selected temperatures, right? And I can just plot it. And I have to say that in those calculations, I do take running in the splitting or the gluon emission, if you want. But since those are lowest order cross sections, for the elastic scattering cross sections, I use 3 levels, and these are fixed couplings. Those are the G's that I quote. More than 15 years ago, I did try to include running G, and in principle you can do it, but I found that it would depend on how you regulate the very small momentum transfer behavior, and ultimately it was dominated by momentum transfers on the order maybe of a few times the Debye screening scale, a few times the Debye screening scale. The elastic scattering cross section, if you're worried about momentum transfer, falls like 1 over q to the 4, and 1 over q to the 4 will trump any logarithmic dependence in alphas. So I decided that it's more transparent just to use fixed coupling for that particular part.
Yes.
Okay. Other questions?
Hello. Hi.
Paul?
Okay, sorry. Any other questions?
There was Paul, I think, or no? No.
Ivan?
Oh.
Yeah. So sorry, then. Let me show this again. Yeah, okay, go ahead.
At your very last slide, you had an increase of the proportional of this fractional energy loss.
Yeah.
And you said the increase was due to the LPM effect. I got a bit lost there.
Yeah. So it takes right the LPM effect, as I said, depends on everything, on the energy of the emitted gluon and then on the transverse momenta. But what the energy in the emitted gluon and the transverse momenta are also depends on the energy of the parton, right? So we do impose the kinematics, we do impose the finite kinematics, those cannot go to infinity. And so it works out that for those smaller energies, you have a different combination of medium lengths and formation lengths of the gluon, which control the LPM effect. It's just because you have smaller phase space, you have more restricted range of formation lengths, and that's how it ends up working out. It's not only the heavy quark mass, because we see the same behavior. I mean, kind of the peak is not exactly in the same position, but we see the same behavior if we calculate light quark energy loss. So for light quarks, it will not continue to increase. It will also at some point turn around. So it's just kind of phase space effects that come into the play together with the LPM.
What is the medium length here in this situation?
Well, the medium length in that's the other thing that doesn't have a good. So it was still 30 to 50 percent centrality. So kind of let's say if we call for central collisions, average medium length from the center to the periphery, 6, let's call it 3, right? There's no good explanation, but let's call it about half of what it's in central collision. So it's about 3 Fermi, maybe.
Okay, thank you.
Okay, there is just one question that was written in the chat. I just read. I don't know if you have the answer now. My question is, since you need to integrate out the spatial information first in the QCD evolution approach, how sensitive are these results to the spatial integration, such as the initial time and final decoupling temperature from the hot medium? Is it possible to integrate it into the hadronic phase to determine the hadronic transport parameters?
For the hadronic, I have immediately the answer for, kind of to very early times now. Once again, it's along the question that Paul said. At very, very early times, whether I vary the initial conditions to start at 0.6 or 0.3, that there won't be much sensitivity. And the reason is, once again, because of the LPM effect and, kind of those kind of space time considerations. It takes a little time. It takes about a Fermi to start building the energy loss. If we make very short media, really kind of the energy loss will be 0 in those very short times. For the hadronic phase, I don't know. So here we essentially run the hydrodynamic evolution and do full propagation. And if it, let's say, starts to hadronize earlier, then we use parton-hadron duality. So we don't kind of cut off at one particular temperature. So it propagates through the full media.
Okay, thank you. Thank you, Ivan, again for your talk. And now we move to the other approach, that is the dub mode. And there will be Roland giving the talk.
Yes, can you hear
Please
me?
share your screen.
Can you hear me well?
Yes.
Yes, cool. Okay,
You
because
can
I had some
full screen.
Yeah, it is. Oh, yeah, you're right. Sorry. Yes, now it is. So sorry, I've had some connection problem this afternoon, so I hope it's going to be okay with the sound and the slides. Okay, so first of all, thank you for the invitation. Today I will address the transport aspects in DAB mode. So I just did one slide to present a bit the model, the DAB mode model. So DAB mode stands for DNB Meson's modular code. It is a simulation that evolves EV quarks on the top of two-dimensional bulk profiles that are given by some initial conditions like Trento or NCKLN. And then the bulk is evolved with some viscous hydrocodes. We use the so-called VUSP hydro. For the EV quarks, for the transport of the EV quarks, we use either a parametric energy loss model or a relativistic Langevin dynamics. Then at the end of the evolution, we hadronize the EV quarks using fragmentation and or coalescence. The main analysis that we addressed were the array versus V2 challenge, the study of anisotropies with the cumulants, and the exploration of new observables related to anisotropies. And more recently, we performed a system size scan at LHC. Okay, now let me start with the transport equations. Okay. So first, the energy loss. For the energy loss, we use a simple parametric model that comes from jet physics. It allows to easily test different parameter dependencies, like the temperature or the velocity of the EV quark, and to include some energy loss fluctuations through a single random variable that is here. But so the good part of this modelization, it is that it is quite simple, but the down part is that it does not tell us much about the underlying physics, the radiative and collisional components of the energy loss, for example. Okay, let's take a deeper look at this modelization. So the first term that I will tell you more, it's the last term actually, which is the gamma flow factor, which is here. It allows to take into account the boosts from the medium cell to the global laboratory frame. We first used a formulation that came from jet physics that we found in this paper, but we soon realized that it was too limited to high momentum part of the physics. So we rederived this formulation without assuming the momentum to be much larger than the mass, and we got this new formula that is written here. And we tested these two expressions on the observables, and what we saw is that it gives almost no difference with the area A, but it gave a little difference or a little bit higher results for the V2 and the V3 with the exact formulation. And the impact was limited at momentum smaller or equal to 3 times the EV quark mass. Okay, now about the parametrization that we use. So we tested 5 different parametrizations at the beginning of the demo simulation. The first two parametrization that we tried are quadratic in the temperature. It was inspired by conformal IDS-CFT calculations that we found. So one is simply the quadratic dependence on the temperature, and the other one also includes a velocity dependence. The next two that we tested were found in the area A or inspired, sorry, not found in an analysis of the area versus V2, which showed that a temperature independent coefficients, the temperature independent coefficients are favored to better fit the two observables. So we decided to just take one constant parametrization and one constant time velocity dependence. The last parametrization that we tried is a bit more complex and has more complicated dependence on the temperature and the velocity, and includes a drag force that came from an holographic model that described lattice QCD thermodynamics. So, oh, sorry, I just forgot to tell you that. So, as you can see, each of these models include a proportionality coefficient that we need to fix to compare them. So, what we did here to make these plots here is to fix these parameters to get the same area A at 10 GeV, at transverse momentum 10 GeV, equal to 10 GeV. So what you can see is that the red and blue curves, which corresponds to the velocity independent models, gave us the best results at intermediate and high PT. Another thing that you can see is that the temperature dependence does not play any role for the area A. For example, between the red and blue curves, the blue curves includes a quadratic dependence on the temperature, and you see that they gave the same result. But it's not the case for the V2. In the V2 case, we see that the temperature dependence plays a role. This was already observed in other analysis. So finally, we choose to only keep the constant parametrization and the simple quadratic temperature dependence. Okay, so the last term of this parametrization tried to tackle the energy loss fluctuations. So the idea is that it is a random variable that takes only one value for each EV quarks, And this random variable is given by, we tested 3 different probability distributions. One is uniform, one is a Gaussian, and one is linear. So what we observe, including these effects, is that it has a small impact on the nuclear modification factor, but it has a large impact on the Vn, and it tends to quite lower the V2 and V3 at low and intermediate PT, which was not quite relevant within our model as compared to the data. So we decided to not, at the end, to not include the energy loss fluctuations to our modelization. Okay, so now it's done with the energy loss. Now about the Langevin dynamics. So we use the usual relativistic Langevin equation, as you already saw many times today. We perform all the necessary boosts, and we use the relativistic Einstein fluctuation dissipation relation. For the diffusion coefficients, we use 2 different parameterizations. One comes from Moore and Tini. It's the famous QCD plus HTL model that gives this formulation here. And we need to fix the 3 parameter which is called K here, K and T here. The second modelization that we use for the diffusion coefficient is it comes from Gaussian and HLN, which is a QCD plus HTL collisional model that Marlene told you before. And so we got a drag from this modelization, and we decided to add as well a proportionality coefficient to use it concretely. Okay, so if we look a bit what kind of diffusion coefficient we get with this formulation, with this model, we see that the Moore and Tini model is a bit more compatible with the lattice QCD results, and that the Gaussian and HLN is a bit too low as compared to this. And as compared to the other models, we are more on the low side of the value for this diffusion coefficient. So one important thing that I need to tell you about all these models has how we do the calibration for the 3 parameters. So you saw that for each transport model, we have 1 free parameter. And we fix them using the most central array data. And we use high PT data for energy loss and intermediate PT for Langevin. So we fix it and we use it once and for all our calculations. Yeah. So let me show you some comparison that we got with using these 4 models. In red and blue, you see the energy loss curves, and in green and orange, you have the Langevin curves. So what you can see is that at high PT, we obtain quite similar trends, and that at low PT, the energy loss gives much more suppression that we are expecting from the data. For the azimuthal anisotropies, what we observed is that the Langevin Moore and Tini models gives us the best results at low PT, while the constant energy loss model gives us best results at high PT, and that in general we underestimate the Vn at high PT. The results I showed you here was obtained with MCKLN initial condition and only with fragmentation. Tomorrow I will show you results with Trento and including coalescence, and you will see that we get much better agreements with the data. Okay, let me conclude. So we observed the multi-scale behavior of EV quark physics. Langevin was better at low PT, energy loss at high PT. We also concluded that within that mode, the temperature and velocity independent energy loss model was favored, and that the Moore and Tini diffusion coefficient for the Langevin dynamics was also favored. Thank you very much.
Okay, thank you, Roland. Other questions? sorry, I missed the by Moore-Antini diffusion coefficient that is so close to lattice QCD. To what do you refer? Because it's not the standard paper on Langevin.
I'm sorry, do you mean this bench?
Yeah, because in 2005, but I remember in 2005 or 2004, they just used the QCD scaled approach. They used PQCD and then multiplied by a K factor. Is this work that you refer to or other works?
I think so, yes. It was, wait.
Okay, so maybe it's some upscaled value.
Yes, it was the 2005 work.
Okay. Paul?
But then just to go on, Roland, so you also refer to the precise value that they kind of have, they have a favorite band, okay, this Moore-Antini. And is this you refer to, or?
The precise band, sorry, what?
Well, they do not fix it precisely from theoretical viewpoint.
No, they didn't. They just obtained this 1/2 pi t dependence. And there is one coefficient, one free parameter that is how to say, free to fix.
Okay, concerning the approach, I want to insist, I mean, since the second time it is said that the North model is below the L lattice QCD data. I think it is plainly true.
Within that mode. Here.
Sorry?
Within our model.
No. It is true in the absolute sense if you only consider elastic energy loss. Okay.
Yes.
But
yes,
we have also a cocktail model where we also include a radiative component, which has very little impact on the DS. And then basically we start being compatible also with this data.
It's true. I wrote here that it was only the collisional model that you sent me and not the full one.
Well, you didn't ask for it.
Yeah, actually I did. I used it, but I didn't have the result to show here, so okay. I didn't show it.
Okay, some other question? If not, thanks again, Roland. And we go to the last talk of this session. That is the one about the QJet approach. There should be Jinfeng Liao.
He's not here. I'm not sure we have.
I'm here. No worries.
Oh, you are there now. Okay.
No, I have been around. Sorry, but I missed yesterday because I had to teach and things like that, so I wasn't able to join yesterday. But okay, so let me start sharing my screen.
Yes.
All right. Okay, so can you see the screen?
Yes.
All right. Okay, should I get started?
Yes, just start.
All right. First of all, let me thank all the organizers for this opportunity to discuss some of our work related to SteelJet 3. And of course, it was kind of unfortunate that we were not able to get together in person. And it's glad to see many of you whom I haven't seen for a while. Okay, so let me be brief. I think it's getting late for people here in Europe and really late for people in Asia. So let me try to be brief. So here, thanks for your interest in knowing something about the SteelJet stuff. Just a very, very quick kind of quote unquote history. That really means Columbia University Jet. That's how Miklos initially named it. But we didn't have some intention to change it because it has been around for more than a decade by now. So I think it started with 2010 or 11, in which Miklos and students tried to modernize basically the DGLV energy loss and also want to address the heavy flavor problem that was in the old DGLV. And then that was quite successful. And then SteelJet 2 around this time with the student Jet 10. That was the first version where they implemented really the realistic bulk, namely, for example, using the Vishnu Hydro and some of the HTL formulas, running coupling, recoil, everything. Again, you can look into their papers. This is when I got involved. So we started some collaboration around 2014. The main idea that brought us together was to implement some non-productive effect from the medium side, not from the jet energy loss itself, but from the medium side. The reason for that was because obviously with the COGL2, there was problem describing data quantitatively, and I will show you some of that later on. And then that's around this time, and I think that turned out to be very successful, both I think from a theoretical point of view and a phenomenological point of view. And then that was the latest stage, which we called COGL 3.1 or CIPJET. That's after 2017, where we fixed a number of issues in this version. And I think this now a mature framework had passed the global constraints from various data that I will show you in a moment. So these are the people that are involved in this COGL 3. Shu Deshi, who is now a postdoc at McGill, and of course Miklos, me, and Jie Chen. Jie Chen now is on the Wall Street making big money, using the numerics for different purposes. So these are some of the relevant papers. Okay, so just a really very quick discussion of why we want to do that. Well, just to remind everybody, QCD is difficult. Okay, we say we have a Lagrangian of quarks and gluons, but in the vacuum you don't get to see them. You see something that emerge from quarks and gluon, namely the hadron. And the quark and gluon are strongly and deeply bound within the hadron. They cannot escape. That's of course one of the biggest puzzles within the standard model. One of the ways to look at this is to say that QCD vacuum is so strongly coupled that you have essentially an emerging phenomenon that's like a dual superconductor, where your gluon fields organize into magnetic degrees of freedom, and even not only that, and they condense, just like Bose-Einstein condensation of some magnetic charged object. And that indeed could explain the formation of color electric flux tube and linear potential and all that. Again, I want to be very brief, and I don't want to go deep into that. Just want to say that there is reason to believe that there is strong emerging magnetic activity in the QCD vacuum. Now, making that connection with what we do in the heavy-ion physics, remember a lot of the initial motivation to do heavy-ion physics is just to sort of get away from that. Okay, you want to heat the whole system up so that you eventually get back to a system of just quarks and gluons, and you want to go away from this confinement regime. So that was that was the hope. But on the other hand, it's not clear, whether you can really get away from those degrees of freedom, and that's an important question, because when you're dealing with a complicated quantum system, perhaps the most important question is what are degrees of freedom. Now you're given this, partition function or whatever, theory of everything for QCD. You have a QCD action. You want to integrate over all your gluon field, quark field. There are only two strategies basically. Either you use the real computer with brute force, okay, that's of course the lattice QCD, or you want to build effective model that start with the right degree of freedom, and then that of course bring the question: what are the most important relevant degrees for enforcing confinement? Now, I think there are many good examples already. Remember that QCD or nuclear world in general comes from quark gluon, but when we are dealing with hadronic physics, we never use quark gluon, or not never. We try to use just hadron as our degree of freedom. And then, for example, if you are doing nuclear physics, nuclear structure, you don't want to use quark and gluon. You use say emerging degrees of freedom, the nucleon and the pion and so on, right? So we already have many good examples where you should use the right degrees of freedom. And there is this famous quote from Weinberg, who said that you can use any degree of freedom that you like to describe the physical system, but if you choose the wrong one, you will be sorry, basically. Okay, so that's all. These are just some motivating talking points. So coming to quark-gluon plasma again, remember that the old expectation from late 1970s and so on is that you start with the confining vacuum, you suddenly heat it enough that you get into a simple quark-gluon plasma. That turned out to be not entirely true. From past 2 decades at RHC, we have figured out pretty much a region in the 1 times TC to about 3 times at most 4 times TC. In this region, the system is what we call a nearly perfect fluid. or nearly perfect liquid, which apparently is more strongly coupled than we thought. Okay, so that means this region really is not in the asymptotic freedom region yet. Okay, it's perhaps closer to vacuum. It's more resembling the vacuum, and that of course raises the question: what are the right degrees of freedom here? Okay, are they going to be simple quark gluons? Are they going to be remnants, of hadron, or what do we have here? And that is even more interesting when you look at the lattice data for thermodynamics. Okay, so these are basically let's say first principle result for entropy density over T cube and the so-called Polyak loop, which tells you the amount of suppression on countercharge. Now, what do you see that in the entropy that is liberated toward a high temperature phase very quickly, around 150, 160 MeV. Now, if you look at the Polyak loop, it goes up very, very slowly. If you go all the way from nearly 0 to 1, that means you have a full liberation of color. So that kind of mismatch or discrepancy is telling us something. Namely, you get a lot of degrees of freedom that are liberated into the thermal system. But on the other hand, your colors are not very free yet. So that's what motivated a number of us, for example, Rob Pisarsky and also Edward and me and other people to speculate that the quarks and gluons are not really the dominant degree of freedom in this region. There's something else, okay? And that something else are magnetic degrees of freedom. We call it, magnetic monopoles. There are some topological construction of the gluon field that are important as strong coupling. And there is this general rule between electric and magnetic degrees of freedom. That's the famous Dirac condition. And that seems to all make sense because when you go down to TC, electric coupling becomes strong, your magnetic coupling becomes weak. So hopefully that's where magnetic degrees of freedom become the dominant degrees of freedom and a better description of the system. And that also makes sense in because it can connect naturally to the confining vacuum. If you're cooling down a system of many magnetic charges, it's more natural to expect them to condense and become a dual superconductor in the vacuum. So that seems to be making a lot of sense to us. So we propose this scenario that in this region, you are going to get not only just the quarks and gluons, but also quite abundant number of those emerging magnetic monopoles. So that's the basic picture we have in mind. And we do have some evidence from lattice results and from effective models, which suggests that the number density of those objects strongly increase. So this is the number density of monopoles divided by T cube, strongly increase toward TC. Now this is not QCD. I should make it clear. This is an example from SU2 pure gauge theory. Whether or how you define and count monopoles are of course still a big deal, a big question for lattice and for models. But let's say there are suggestive hints that this kind of pictures make sense. Okay. All right. So how does that get married together with for example hard probe, jet energy loss, and everything? That started from another aspect that I was involved in some time ago, namely trying to understand the geometric anisotropy of jet energy loss. So everybody understand that if you have a a fireball like an elliptic shape, of course the path length for jet going in plane and a path length going out plane would be different. That means you should have different amount of energy loss in and out. So that gives you an anisotropy, which people just call V2 for jet, for high energy particle. Okay, high PT hadron. Around that time, 2008, there's a big discrepancy between all the models with experimental data from physics. So that got us interested why suddenly all these models work very well for RAA, for centrality dependence, PT dependence, and so on. Why suddenly it wouldn't work at all for V2? So that's when we got interested in this. So we had this paper which we suggest that maybe there is a very non-trivial temperature dependence of the jet medium coupling. And of course, we were motivated by the fact that there is the emergence of this component, namely the magnetic component. Why they would help the jet quenching? Well, again, because of this Dirac condition, a magnetic particle and the electric particle is always strongly coupled. So if you suddenly get a lot of monopoles around in the near TC region, you would have a strong enhancement of jet energy loss in that region. or jet medium coupling. So that's sort of the motivation of that work. And what we did essentially in that work was phenomenological. We say, suppose you get this kind of bump or non-monotonic behavior of jet medium coupling, which we call kappa in that paper. We just construct some phenomenological model that say you have, some, constant jet medium coupling, and suddenly you get a bump. And we see what's the phenomenological consequence of that bump. And we can vary the bump up and down. What you see is that what you need is about I think 2 to 5 times stronger kappa in this region if you want to really explain that V2 data quantitative from the Phoenix at the time. So that was 2008, 2009. So basically we concluded from that paper that, jets are quenched about 2 to 5 times stronger in the near TC region, okay? And that we believe should be a interesting evidence or at least hint for magnetic degrees of freedom. But that paper was relatively kind of simple or primitive in terms of phenomenology because we didn't use at that time, and many of the things were not available yet. And so more recently, starting 2014, we tried to combine the idea from the magnetic scenario with the more sophisticated modeling framework like the COJET. Okay, so COJET 3 again. What is making that modeling different? It's the microscopic picture of the medium. Okay, we're using a medium that include both quark and gluon, which are suppressed by that polyak loop, and abundance of monopole in the near TC region. Okay, so this picture just shows you the difference. For example, in the COJET 2, you have only quarks and gluons. For each given temperature, you take your lattice pressure or entropy density, you divide them between quarks and gluons. Usually that's done based on, let's say, a weakly coupled QGP or cosy particle model. Let's say, I think many of the modeling that were discussed today use the cosy particle picture. So basically this quark cosy particle and gluon cosy particle for weakly coupled QGP. Now for this strongly coupled or semi-QGMP, we have 3 components: quark, gluon, and monopole. And at high temperature, it's dominated by quarks and gluon as usual. But when you're going into the near TC region, that component emerge and become important. Okay, so that's what goes into the COJ3 medium. Okay, so
you have 5 minutes more or less.
How many minutes? Sorry.
5.
5. Okay, thank you. Yeah. So then that's the crucial question: how you do this? I mean, you cannot do it arbitrarily. Okay, so we try our best to use all kinds of lattice information. For example, this Polyakov loop, we borrow that Polyakov loop from lattice to suppress the quark gluon contribution, and roughly using this simple formula, the quarks are suppressed by L and gluon suppressed by L squared. These are not exact, but we're just borrowing that picture from the semi-QGP from Rob Pisarski and collaborators. The magnetic density would be whatever that are not in the electric density. Okay, so you use 1 minus the electric fraction. Alpha is running coupling. Okay, and then you have screening mass, which is important in the DGLV formulation for the energy loss formula for the scattering. So you have electric screening, just the Debye formula. Of course, that depends on the electric density. The magnetic screening we don't know, so we use some magnetic scaling formula with the unfixed coefficient. Basically, there are two coefficients. There are 2 parameters: coupling constant at TC and the magnetic screening coefficient. Now, the total pressure or total density are fixed according to lattice. So we're not overdoing the medium. We're not having too many particles in the medium. Okay, so that everything was was done, to the best we could. Okay, and these screening methods are also being compared to lattice just to make sure that we're not far off from, what we know from lattice. Okay, so phenomenology. So I should be done in a few minutes. So in this, especially in this new paper in the newest generation of COJET, we did a global analysis with all RICA data we can find. So there are 2 parameters that I mentioned: running coupling the TC and the magnetic screening coefficient. We used 12 sets of light flavor data from RIC all the way to LGC, 5 TeV, all kinds of different centrality and RAA and V2. Okay, you can see that that is the global chi-square against all those data. It's a huge amount of data if you think about it. Okay, now if you only look at RA, that's how it looks like in the parameter plane, the chi-square. If you only look at V2, you can see this. V2 is a little more sensitive and more constraining, obviously. And if you use both RA and V2 together, that's the map we get. So you can identify the most optimal parameters for the C and alpha in our modeling. So that's how we fix them. Again, we use the global constraints. Now, you may say, well, that seems to be trivial. Then that means you are bound to get good description of data. But that's not so trivial, actually, if you think about it. You can do the same game for other models. Let's say we take, COGL2 weak QGP. You do the same game. You use those data, data to try to minimize your chi-square. But the best you can do is only to about 8 to 15 for weak QGP. So you can see there is some difference. There is a quantitative difference. For this model, you really can make chi-square per degree of freedom to be, on the order of 2. So that means, quantitative speaking, that certainly provides a better description of all this data. And the magnetic component in this SQGMP is very crucial. Okay, so those are done with light flavor. So you can use actually the heavy flavor. Let's come to the topic of this workshop. We can use heavy flavor observable the independent test. So we're focusing for now the high PT region. Okay, you can see these are the tests we have done, in these papers with the CMS, D and B, and also V2, RA and V2. And we have essentially not more calculations in the paper. And I think over the last couple of years, we have provided our data to various collaboration, CMS, ALICE, and also Atlas for various comparisons. I think they all work quite reasonably well. But again, I emphasize these are independent tests because our 2 parameters are fixed with the light flavor data. And another important question is whether you can describe the hard and soft sectors together. So that means you want to test your bulk soft particle production and high PT energy loss together, and that seems to be working well as well. But this is difficult because we have to do event by event simulation to calculate V3. But it looks to to be very good, I would say. So that's another important consistency check. Namely, you want to describe both the soft and hard observables within that framework. Now, the last thing I want to talk about is the transport coefficient. That's my understanding that today's discussions are focusing on what goes into a different modeling framework and what are the transport coefficients, especially the heavy flavor diffusion, for example. Now, a COGL, of course, by itself is just a hard scattering modeling, the jet energy loss modeling. But we try to push the boundary to give us some indication about transport coefficient, which typically are in the soft region. We try to push that jet energy from 30 GeV down to about 3 GeV. So because we have a microscopic picture of how many quarks and gluons molybs are there, and the cross section, we can use that to to estimate at least, for example, what is the Q hat and what is the shear viscosity over entropy density. So that's how it looks like. You can see if you have a 30 GeV jet, the Q hat over T cube looks like this. It's divided of a strong peak, and it's consistent with, let's say, some of the super Yang-Mills holographic model, where weak QGP will be like this. Now, if you push that energy, jet energy or parton energy down to 3 GeV, that's how it looks like. It goes down a lot, but still it develops a peak. Okay, and you can use that result Q hat to or scattering rate in that region to estimate the eta over S. So that's what we get. Okay, so this shows you the fraction of different particles. When you go down from high temperature to low temperature, quark gluon fraction goes down quickly, and the molecule fraction goes up quickly, and that helps enhance the scattering. And you can see the shear viscosity goes down like this, and this is consistent with what you would need for successful description of the soft bulk evolution. So the last slide here, I'm showing you the 2pi TDS that we extract from COJet. Well, really what we did here in this curve, so that's the COJet band, the red, is just to use this Q hat to make to use the Q hat to infer that. But that gave us some useful indication of what that would look like in COJet kind of microscope picture. So these are various other models or other or lattice results up to this moment. So you can see this is relative on the low side. Of course, right now there's still a huge span of different results. But I think this seem to be in a reasonable regime, and phenomenologically, we are going to implement this into a Langevin dynamics, which we started in this paper. So we'll see how that goes. So with that, I will stop here and take questions. Thank you very much.
Okay. Thank you, Jingfeng, for your talk on the QJet. And
Can I ask
questions?
Can I ask a question? I don't have a hand.
Don't worry, just ask.
Okay, so let's ask without the hand. Hi, Jingfeng, thanks for the talk. So I had a few questions. If I may, if you go to the previous slide, you were showing kind of two Q hats over T cubed, and kind of let's forget about the modeling of the medium. But I noticed the difference in the overall magnitude that you show, depending on whether you have a 3 GeV or you set the one in the bigger panel is 30 GeV. So do you use do you include energy logarithms in your definition of the Q hat? In other words, does your Q hat depend on the energy of the jet?
No, that's right. That's exactly what I'm showing here, right? So 30 GeV, this is the curve for the, so this 30 GeV means the parton energy.
Yeah.
And this is 3 GeV, 30 is depend, right? It strongly depends on that.
Yeah, okay, all right. Then kind of what you quote for those coefficients. So if you go then to the next slide, the other thing that I meant to ask you is, how do you quote those coefficients, right? Because with all the medium non-perturbative input and modeling of the medium, ultimately CU jet is based on DGLV, plus I believe it has collisional energy loss, and it's a perturbative calculation. And so you technically cannot take it to the zero energy limit. And if you use a pocket formula like certain number of pi divided by Q hat divided by T cube, is that what you really used to plot this? I'm just kind of curious how you can provide a quote for that, but that's not something that comes out of your calculation. You just borrow the pocket formula.
You're completely right that, in principle, all this COJ Q hat, these are, or the Q hat itself has a formula which is meant for high PT particle or high PT particle. That I of course completely agree.
Okay.
So that's, that's
so
why
on the next figure, kind of your band will actually depend somewhat on what jet energy you take, and in principle, you can take the zero limit.
Correct. No, that's right. So both the eta over S and the diffusion are calculated with pushing that Q hat or jet energy down to 3 GeV, which is getting close to the medium particle thermal energy. So that's
okay.
Because we don't want to go.
Because I took it literally, right? Because it's still a perturbative approach, and as I said, you cannot really push it. So similarly, my question was, I know you did not discuss it here, but I saw in the homework figures that you provided like a drag coefficient. And once again, I was wondering how will you talk about it maybe tomorrow? I was wondering how you define it, right? Because it's a local quantity per Fermi. And so what did you actually quote? I mean, is it collisional drag? Is it radiative drag? And if it is, what prescription did you actually use?
Sorry that it has been a while. But I think if I remember correctly, when we provided those, that drag include both collisional and radiative.
But how did you define it? Because radiative processes are non-local.
Perhaps I think all we do is to connect that with Q hat. I guess that's if I remember correctly. Because really that what we in our formulation we basically define of course Q hat, and other quantities are connected to Q hat.
So maybe it's I don't know.
Like to interrupt here the discussion just because the point of view is of course very interesting and relevant. Maybe it's better to continue just after this session in the general discussion session. There is a question from Paul.
Yes, Jim, thanks a lot for this nice presentation. I just have a question. Since somehow you advocate a new type of degree of freedom close to the transition point, would you have also some kind of specific physical effect associated to this new degree of freedom? You know, something there's a V1 for this early magnetic field. I mean, is this really something that you need the magnetic field to explain mostly? What should be the specific effect associated to this magnetic monopoles around TC?
Mm-hmm. No, these are good questions, but of course, just want to be sure the monopole that we talk about here, of course, the chrome monopole, you may say it's just some complete gluon composite, but they are difficult to catch because they don't carry some of the usual charge like the Maxwell electric charge or baryon charge or anything like that. So it's kind of hard to directly see their effect, and that's why, of course, we have been working very hard with the energy loss, which gave some indication of their existence. Yeah, that's a good question. I don't have very concrete idea about how you can directly see their effect, because generally speaking, all the gluon kind of effects are hard to directly observe. You have to observe those effects through their influence, for example, on the quarks or hadron production, I guess. But that's a interesting question. Yeah.
Yeah, because each time you advocate for a new degree of freedom, one has to be a bit careful as well. But okay, thank you.
Mm-hmm.